Today's lesson is going to focus on the common ion effect. This is an application of solubility equilibria. Once we know that an equilibrium is established with a substance that doesn't dissolve well in water, we have the ability to shift that equilibrium to the left, to the right, using the principles of Le Chatelier's principle. So let's consider a saturated solution of silver chloride. And when we have this saturated solution, we know that we will see some solid floating around in your beaker, let's say. And then we know that some of our ions will be dissolved already. We don't see them, but we consider the simulation that we saw the other day in class, and we know that the rate of dissolving is going to equal the rate of ions coming out of solution and reforming the solid or precipitate. So now let's add a common ion to the saturated solution. So if we added a few drops of HCl to the equilibrium mixture, we would be increasing the concentration of chloride ions. So if we come over to our reaction itself, we can consider that we're going to be increasing this concentration of chloride ion. And we know, based on Le Chatelier's principle, that if I increase this concentration, the system wants to offset the stress. It's going to shift and create more reactants, or shift to the left side to make more reactants. So if this is happening, because the solid substance is on the reactant side, we would actually notice more solid forming due to that increased concentration of chloride ion. Now, the same would be true of the silver ion. So let's pretend that we added silver nitrate or silver acetate, something else that would increase the concentration of silver ion. We would notice the same thing. So the chloride ion would be called the common ion in this case because it already exists in our equilibrium mixture. The big message for you to take home is this italicized phrase right here: common ions decrease the solubility of substances. So even though we know at 25 degrees C, a certain amount of silver ions and chloride ions can dissolve from silver chloride, if there is a common ion, Le Chatelier's principle says that the equilibrium will shift to the opposite side, and you will always decrease the solubility of those ions. So before we do a question with the common ion effect, let's just recap our KSP lesson, and let's calculate the molar solubility of iron 2 fluoride in water alone. So this is exactly the same as the previous lesson, where we're just taking these solids and seeing how far they're going to dissolve in water. So the first thing we must do is write out our dissociation equation for iron 2 fluoride. So we're going to have FeF2. This is going to be a solid. We assume that it's going to set up an equilibrium. We know the charge on iron is +2. It's telling us right here. And that some of that is going to dissolve. And then we know that we have fluoride ion coming off. And we remember that the fact that there's 2 of those fluoride ions means we have to balance that stoichiometrically. When this happens, we know that whatever amount of iron ion gets dissolved, twice the amount of fluoride ion will also dissolve. So we set up our KSP expression, and we equate that to concentration of iron ion at equilibrium times the concentration of fluoride ion at equilibrium squared. We go to our data booklet, we look up the KSP of iron 2 fluoride. If it's not there, we just hop onto Google, find it there, and we get a value of 2.36 times 10 to the negative 6 as the KSP of iron 2 fluoride. This is equal to X for iron, 2X squared for fluoride ion. We expand this out, so we get 2.36 times 10 to the negative 6 equals, so again, we're going to have x here. 2x squared is 4x squared. Multiply that together, and we end up with 4x cubed, equaling our KSP value. We solve for x, and we're going to take the cubed root of our KSP value, so 2.36 times 10 to the negative 6, and we divide that by 4. Bring it on over here. X is equal to 0.00839 molar. Okay, so that's how much will dissolve just in water. Now let's do an extension of this example and add a common ion into the mix. So our second example will focus now on a common ion. So what is the molar solubility of iron 2 fluoride? So again, the exact same substance, but now in a solution of 0.025 molar sodium fluoride. So this is now saying we have a beaker and we have some sodium fluoride in here. And we've got, as a result, some sodium ions floating around, some fluoride ions floating around. We assume that this is dissolving decently in there. It's not that that has low solubility. And then here we come with our iron 2 fluoride, our FeF2, and we're going to try to dissolve that solid into the solution that already has a common ion present. So we don't care about the sodium ion concentration, but we sure care about the fluoride ion concentration because we know it's not going to allow FeF2 to dissolve as much. So the first thing that we need to do is we need to figure out the concentration of sodium fluoride. And so we take our common ion, substance, and we know that this is going to dissociate into water and form sodium ions and fluoride ions. And we have to figure out what is the concentration of fluoride ions. So the assumption here is that they always are dissolving fairly well in solution. Okay, usually the common ion has good solubility. Okay, so it's fully dissociated and the ions are floating around freely and not reforming a solid substance. So what we look at here is the fact that this is a 1-to-1 ratio of ions, those sodium ions and those fluoride ions. And because we're talking about a molar concentration, when I want to figure out the concentration of fluoride ion, this is a 1-to-1 ratio. Now, if there was a coefficient of 2 in front of fluoride or a coefficient of 3, I would be multiplying this initial concentration. But because it's a 1-to-1 ratio, this concentration of fluoride ion is also 0.025 molar. And this is very important that we obtain that concentration initially because we now need an ice chart. So remember, in here, this initial concentration is now 0.025 molar. I now have an initial concentration of that fluoride ion. So we go back to the substance in question, okay, which is FeF2, and we are asking, what is the solubility of this now when we have some sodium fluoride in the beaker already? So we set up our dissociation equation just like we did in the previous example. And now we have to set up an ice chart because I have an initial concentration of the common ion. We still do not care how much solid we dump into that beaker. We know it doesn't matter how much solid we put in. We just assume it's saturated and the ions will dissociate to the extent that they can in that given temperature. So initially in this beaker, I have no iron ion, right? We can see that. So my initial concentration of iron is 0, but my initial concentration of fluoride ion is right over here. So I have 0.025 molar of fluoride ion. Over time, this FeF2 is dissociating. The iron will increase by X and the fluoride will increase by 2X. So that at equilibrium, I end up with X for iron and I end up with 0.025 plus 2X for my fluoride ion concentration. So we come over now and we set up a KSP expression. And so the KSP is going to still be equal to the concentration of iron times the concentration of fluoride squared. And our K value hasn't changed. It's still 2.36 times 10 to the negative 6. And right there, we should be suspicious that we have a really small K value. So don't forget about some of these things that we learned in gas equilibrium. If you think that you have a small K value and you know the initial concentration, why wouldn't you check out whether we could neglect this X term right here? So let's off to the side, see if we can neglect anything. So we're going to check for small k. Hopefully you can read my writing. And we're going to take that initial concentration of 0.025 and we're going to divide by 2.36 times 10 to the negative 6, and it is greater than 500. So we are very happy. And what this means is we can neglect that change in X on that product side. This is good news because this makes our math very, very easy. Iron is going to have a value of X that we insert. Fluoride will only be 0.025, but don't forget to square it. Okay, you still need that coefficient of 2 coming off of the dissociation equation, which squares everything. We're going to set this up now. So X, we just have to do some rearranging. X is equal to 2.36 times 10 to the negative 6, and we're dividing by 0.025 squared, and we get an X value of 0.0000378 molar. Now, don't forget the value that we got in the first example. That first example, the molar solubility in just pure water was 0.00839 molar. And now we've gotten a value of 0.00378. So it just proves what we knew theoretically, that the common ion affects the solubility equilibrium by shifting it to the left side, the reactant side, and it always decreases the solubility of the ions in a saturated solution.